You have been lied to about space your entire life. Not about the stars, not about the planets, about the cold. You were told space is freezing, that you would turn to ice the moment you stepped outside a spacecraft. That is wrong. And the truth is far worse. Space does not freeze you. It does something more terrifying. It strips away every single mechanism your body and your machines use to manage temperature. No air to carry heat. No ground to conduct it. No atmosphere to buffer the difference between blinding sunlight and absolute shadow. Just a vacuum that does not care whether you boil or freeze, because it has removed every tool you have ever relied on to control either one. The real danger was never the number on the thermometer. If this is the kind of science that makes you rethink what you thought you already knew, do us a small favor and hit like and subscribe. It genuinely helps this channel keep going, and we never take it for granted. Are you comfortable? Now, let's begin. Close your eyes for a moment and picture space. Not the stars, not the galaxies, just the emptiness between them. What do you feel? Cold. Almost everyone says cold. It is the single most universal instinct people have about the void above their heads. Space is cold. Space is freezing. Space is the coldest thing there is. You learned it before you could spell the word vacuum. You saw it in every movie, every documentary, every classroom poster of an astronaut floating against a black background with a caption that said something about temperatures hundreds of degrees below zero. The idea is burned into you at an almost biological level. Step outside a spacecraft without protection and you freeze solid, instantly, completely, like a glass of water thrown into the Arctic wind. That image is wrong, not slightly wrong, not oversimplified, fundamentally, structurally wrong in a way that hides the real danger of space and replaces it with a cartoon version that makes people feel like they understand something they absolutely do not. Here is the first thing you need to know. The sentence, "space is cold," does not mean what you think it means. On Earth, when someone says it is cold outside, everybody understands the situation. The air around you is at a low temperature. That air touches your skin. Heat flows from your warm body into the colder air. You feel that transfer as a chill. If the air is cold enough, and the wind is strong enough, and you are exposed long enough, your core body temperature drops, your organs begin to fail, and you die. Hypothermia, frostbite. These are the dangers of cold on Earth, and every one of them depends on one critical ingredient, a medium. A substance surrounding your body that is colder than you are, touching you, and pulling heat out of you through direct contact or moving currents. Space does not have that ingredient. Space has no air, no gas, no fluid, no substance pressing against your skin. The spaces between objects in orbit, between planets, between stars, are not filled with cold air. They are filled with effectively nothing, a vacuum so thorough that in low Earth orbit, a cubic centimeter of space contains a few stray atoms at most. Compare that to the air you are breathing right now, which packs roughly 25 quintillion molecules into that same volume. The difference is not a factor of 2 or 10 or 1,000. It is a factor of trillions upon trillions. For all practical purposes, space is empty. And empty cannot be cold, not in the way you mean it. Cold requires a substance with a temperature. A vacuum is not a substance. It is the absence of one. Asking what the temperature of a vacuum is resembles asking what the color of silence is. The question does not apply the way your brain assumes it does. This is the first crack in the wall. The lie you have been told is not that space is dangerous. It absolutely is. The lie is that the danger comes from cold the way you understand cold. It does not. The danger comes from something far stranger and far more difficult to survive. But to see it, you have to unlearn the one thing everyone thinks they already know. Let us start with what would actually happen. Imagine a human being suddenly exposed to the vacuum of space without a suit, no helmet, no protection, just a person and the void. What kills them? Most people answer instantly. They freeze to death. Some say they explode. A few say their blood boils. Hollywood has made each of these options vivid and memorable. Every one of them is either outright false or so deeply misleading that it might as well be. You would not freeze. Not first. Not fast. Not in any way that resembles what you picture. Here is what the physics actually says. In 1966, a NASA technician named Jim LeBlanc was testing a spacesuit inside a vacuum chamber at the Manned Spacecraft Center in Houston, Texas, the facility now known as the Johnson Space Center. During the test, a hose disconnected. The pressure inside his suit dropped to nearly vacuum levels within seconds. LeBlanc was exposed to conditions that approximated space. He later reported that the last thing he remembered before losing consciousness was the sensation of saliva boiling on his tongue. Not freezing, boiling. He passed out roughly 14 seconds after the pressure loss. His team repressurized the chamber, and he recovered fully. That event is one of the most important data points in the history of space medicine. It tells us exactly what the sequence of danger looks like for an unprotected human in vacuum, and cold is not at the top of the list. The first threat is oxygen deprivation. Within approximately 9 to 12 seconds, the deoxygenated blood circulating from your lungs reaches your brain and you lose consciousness. This happens fast, and it happens without negotiation. No amount of willpower extends the window. Your brain simply stops receiving what it needs and shuts down. The second threat is ebullism. This is what LeBlanc felt on his tongue. When ambient pressure drops below approximately 47 millimeters of mercury, roughly 1/20th of normal atmospheric pressure at sea level, the boiling point of water drops below body temperature. Water in your tissues, your saliva, the moisture on the surface of your eyes and lungs begins to vaporize, not because it is hot, because the pressure that normally keeps it liquid is gone. Your soft tissues swell. Gas forms in your blood. Your body inflates, not explosively, not like a balloon popping, but enough to cause serious damage if the exposure lasts more than about 60 to 90 seconds. The third threat is the damage to your lungs if you made the mistake of holding your breath. The air trapped inside would expand rapidly as the pressure dropped, tearing the delicate tissue. The correct response, counterintuitive as it sounds, is to exhale. Let the air go. Holding onto it is what causes the rupture. Notice what is missing from this sequence. Cold, freezing, frostbite, ice forming on your skin. None of it. A person exposed to vacuum is killed by the absence of pressure and the absence of oxygen long before temperature becomes the dominant factor. Animal studies conducted during the Cold War era confirmed this repeatedly. Dogs and chimpanzees exposed to hard vacuum lost consciousness within seconds and died from decompression effects. Their bodies did not freeze during the exposures. Cooling occurred, yes, but slowly, over timescales far longer than the lethal window for oxygen loss. This is the part that bends people's intuition in half. Space is surrounded by a reputation for extreme cold, and yet the actual killing mechanism of direct vacuum exposure has almost nothing to do with temperature. The cold is real, it is out there, but it operates on a completely different timescale and through a completely different mechanism than the one your instincts assume. To understand why, you need to understand how heat actually moves. On Earth, your body loses heat through 3 mechanisms. Every introductory physics course teaches them: conduction, convection, and radiation. These 3 processes are the entire vocabulary of thermal transfer. There is no fourth option. Heat moves through one of these channels, or it does not move at all. Conduction is heat transfer through direct physical contact. You touch a cold metal railing, and the heat flows from your warm hand into the colder metal. The molecules in your skin vibrate against the molecules in the steel, and energy moves from the warmer object to the cooler one. This is why metal feels colder than wood at the same temperature. Metal conducts heat away from you faster. Convection is heat transfer through moving fluid. When cold air blows across your face, it carries heat away from your skin. The wind chill effect is convection. A winter storm is not just cold because the air temperature is low, it is lethal because the air is moving. A calm 20 below zero night is survivable for a time with proper clothing. A 20 below zero wind at 40 miles per hour can kill you in minutes. The movement of the air accelerates the rate at which your body dumps heat into the environment. Radiation is heat transfer through electromagnetic waves. Every object with a temperature above absolute zero emits infrared radiation. You are doing it right now. Your body radiates energy outward in all directions at a rate of roughly 80 to 100 watts under normal conditions. You do not feel this because the environment around you, the walls, the furniture, the air, radiates energy back at you at a similar rate. The exchange roughly balances and your temperature stays stable. Now, remove the air, remove the walls, remove every object within line of sight. Put a human being in the vacuum of space, floating freely. Conduction is gone. There is nothing to touch. No substance to press against your skin and carry heat away through molecular contact. The vacuum itself cannot conduct heat because it contains no molecules. Convection is gone. There is no fluid flowing past your body, no air current, no wind. The mechanism that makes winter storms lethal on Earth does not exist. All that remains is radiation. Your body continues to emit infrared energy outward into space. It is the only channel through which you can lose heat. And radiation, compared to conduction and convection, is slow. How slow? The human body has a mass of roughly 70 to 80 kilograms. It is made mostly of water, which has one of the highest specific heat capacities of any common substance, approximately 4,000 joules per kilogram per degree Celsius. This means that to lower your body temperature by a single degree, you need to lose somewhere in the range of 300,000 joules of energy. At a radiation rate of around 100 watts, which is roughly 100 joules per second, dropping your core temperature by 1 degree would take approximately 3,000 seconds. That is 50 minutes. Nearly an hour to lose a single degree of body heat through radiation alone. You would be unconscious in 15 seconds and dead within minutes from oxygen deprivation. Your body temperature would barely have budged. This is why the Hollywood image of a person flash freezing in the vacuum of space is so completely, almost absurdly wrong. Vacuum is not a cold substance pulling heat out of you. It is the absence of substance. And, without substance, the two fastest mechanisms your body has for losing heat are eliminated entirely. What remains is the slowest one. A corpse floating in space would cool, yes. Over hours and days, it would radiate away its stored thermal energy and eventually approach the temperature of its surroundings. But it would not frost over like a steak in a freezer. It would cool the way a warm stone cools in a dark room, gradually, silently. The vacuum has all the time in the universe. Now here is where the story turns, because everything you just heard might sound like good news. Space is not as instantly lethal through cold as you thought. Vacuum is actually a decent insulator. Your body holds its heat longer than the movies suggest. If that is what you are taking away from this, you are about to walk into the real trap. The fact that vacuum is a poor conductor of cold does not mean space is thermally safe. It means space is thermally deceptive. The danger is not that space rips heat out of you like a blizzard. The danger is that space removes every thermal system you depend on and replaces them with nothing. And the moment you start interacting with the things that are in space, with sunlight, with shadow, with surfaces, with distance from the star that keeps this entire solar system alive, the thermal picture becomes more hostile than any blizzard on Earth has ever been. Think about what temperature actually means when you are in orbit around the Earth. The International Space Station circles the planet at an altitude of roughly 250 miles. Every 90 minutes, it completes one full lap. During each orbit, it spends part of its time in direct sunlight and part of its time in Earth's shadow. In direct sunlight, the exterior surfaces of the station that face the sun reach temperatures of approximately 250 degrees Fahrenheit. When the station passes into the shadow of the Earth and that sunlight vanishes, those same surfaces plunge to roughly minus 250 degrees Fahrenheit. Let those two numbers sit together, 250 above, minus 250 below. That is a swing of 500 degrees Fahrenheit across the same structure. Not between one side of the planet and the other, not between summer and winter, between one half of a 90-minute orbit and the other. The station crosses that boundary roughly 16 times per day. 16 times every 24 hours, the thermal environment of the most complex machine ever built by humans flips between roasting and freezing. On Earth, nothing like this happens. The atmosphere acts as a massive thermal blanket, absorbing sunlight during the day, radiating stored heat at night, circulating warm air from the equator toward the poles, buffering the transition between day and night, so that the temperature at any given spot typically changes by only 10 to 20 degrees between afternoon and pre-dawn. The atmosphere is so effective at this that most people have never once in their lives thought about it as a thermal regulation system. It just works. Silently, constantly, everywhere. Space has no such system. When sunlight hits a surface in space, nothing diffuses it, nothing scatters it, nothing absorbs part of it and passes the rest along gently. The full power of the sun, approximately 1,400 watts per square meter at Earth's orbital distance, slams into whatever it touches with zero atmospheric filtering. And when the sunlight stops, when an object rotates into shadow or passes behind a planet, the heat does not linger. There is no air to hold it. The warm side of a surface can be scorching, while the shadowed side, centimeters away, is brutally cold. There is no transition zone, no gradient, no gentle curve between warm and cool. The boundary between sunlit and shadowed in space is a cliff. This is what your intuition misses when you hear the phrase, "space is cold." The problem is not a uniform low temperature. The problem is a total absence of thermal stability. Space is not like standing in a walk-in freezer, where the air around you is uniformly cold and your body loses heat predictably in all directions. Space is like standing between an open furnace and an open void simultaneously. One side of you is irradiated with the full intensity of a star. The other side faces the deepest cold in the natural universe. And there is nothing between the two extremes. No buffer, no transition, no mercy. Every object in space exists in this condition. Every satellite, every capsule, every bolt and panel on the exterior of the station experiences a thermal environment that is defined entirely by one question. What is your angle to the sun right now? If you face the sun, you absorb energy at a rate that can push surface temperatures far above the boiling point of water. If you face away from it, you radiate into a void whose background temperature is approximately 2.7 Kelvin. Just a few degrees above absolute zero, the theoretical floor of temperature itself. The background temperature of deep space sits barely above the point where all molecular motion ceases. This number, 2.7 Kelvin, comes from the cosmic microwave background radiation, the faint thermal afterglow of the Big Bang that permeates every corner of the observable universe. It is the temperature that an object in deep space, far from any star, would eventually settle to as it radiated its internal energy away. It is not a wind, it is not a substance, it is the floor, the default. the lowest resting state the universe offers to anything that has exhausted its heat sources and drifted far enough from any star to stop receiving new energy. That floor is what every object in space is radiating toward, and the only thing standing between a spacecraft, a spacesuit, or a human body and that floor is engineering, not clothing. Not insulation in the passive sense that you wear a coat in winter. Active, powered, constantly monitored thermal control systems that manage the difference between being too close to the sun and too far from it simultaneously. Systems that must work without interruption. Because space does not give second chances on thermal failure. But let us not rush ahead. Before we see what those systems look like and what happens when they break, we need to go deeper into the thermal contrast itself. Because orbit around Earth, as extreme as it is the gentle version. Orbit around Earth still receives the full intensity of sunlight for roughly half of every pass. The temperature swings are dramatic, but manageable with the right engineering. The real test of what cold means in space does not happen here. It happens when you take one step further from the sun, when you land on a world that has no atmosphere to catch the light and hold it. When you stand at the edge of a crater that has not seen a single photon of sunlight in billions of years. When you follow the solar system outward past Mars, past Jupiter, past Saturn, to the places where the sun shrinks to a bright dot, barely distinguishable from the stars around it. The temperature numbers out there make the dark side of the space station feel like a summer afternoon, and the technology required to survive those temperatures has not been fully built yet. In some cases, it has not even been fully designed. The engineers working on the next generation of spacesuits for NASA's Artemis program have described the thermal challenge of operating near the Moon's south pole in a phrase that should stop anyone who hears it. They said it is like doing a spacewalk inside liquid nitrogen. That is not a metaphor. It is an engineering assessment from the people whose job it is to keep astronauts alive, and the Moon is our nearest neighbor. It is the closest destination beyond Earth that humans have ever visited. If the thermal challenge of walking on the Moon's south pole is comparable to operating inside a cryogenic fluid, then the challenge of surviving in deeper space, in the outer solar system, in the void between stars, is a problem of a different order entirely. The common understanding of space cold is a children's story, a simplified fable about freezing temperatures that hides the actual physics and replaces it with an image that feels dangerous but is dangerous in all the wrong ways. Space does not freeze you the way winter does. It does something far more comprehensive. It takes away the conduction. It takes away the convection. It takes away the atmospheric blanket. It takes away the thermal mass of the ground beneath you and the air around you. It takes away every mechanism your species has relied on for 4 billion years to regulate its temperature against the energy of a star. And then it leaves you alone with that star. No filter, no buffer, no second layer between you and the raw output of a thermonuclear furnace 93 million miles away. Or worse, it leaves you in the shadow of a world, a crater, a structure, where that star's energy cannot reach you at all, and the only destination your heat has is the void. That is the thermal reality of space. Not a freezer, not an oven. A place where both extremes exist simultaneously, separated by nothing, buffered by nothing, and survived only through technology that has to work every second of every hour without pause. The next stage of this story goes to the places where that contrast reaches its most extreme, where sunlight becomes a memory, where shadow is not temporary, but permanent, where the temperature drops to numbers that challenge the limits of what human engineering has ever been asked to handle. The sun is about to get very far away, and with it goes everything that keeps the thermal math survivable. The sun is the only reason anything in this solar system is warm. That sounds obvious. It is not. Because the implications of that sentence, when you follow them all the way to their conclusion, describe a thermal reality so extreme that most people never fully process it, even after hearing the numbers. On Earth, you never experience the sun as your sole source of warmth. You experience it as one contributor among many. The atmosphere absorbs a portion of the sun's energy and irradiates it in all directions. The oceans store enormous quantities of heat and release it slowly over weeks and months. The ground beneath your feet retains warmth from the afternoon well into the night. Water vapor in the air acts as a thermal blanket, trapping outgoing infrared radiation and slowing the rate at which the surface cools after sunset. Even on the coldest winter night, in the most extreme climate on Earth, you are surrounded by stored thermal energy. The air has heat in it. The ground has heat in it. The walls of any structure you enter have heat in them. Cold on Earth is never absolute. It is always relative, always cushioned, always moderated by a planet-sized web of thermal storage and redistribution that operates continuously, whether anyone notices it or not. Remove that web and you get the moon. The moon is 238,000 miles from Earth on average. It orbits the same sun at effectively the same distance. It receives the same solar intensity, the same 1300 to 1400 watts per square meter. By every surface-level metric, the moon's thermal starting conditions are identical to Earth's, and yet the moon is one of the most thermally hostile surfaces in the solar system. Not because it is far from the sun, because it has no atmosphere. The lunar exosphere, the technical term for the vanishingly thin shell of gas surrounding the moon, is so sparse that it barely qualifies as matter. NASA describes the lunar environment as containing roughly 100 trillion times fewer molecules per cubic centimeter than the air at sea level on Earth. For all meaningful thermal purposes, the moon's surface is exposed directly to the vacuum of space. Nothing stands between the regolith and the sun. Nothing stands between the regolith and the void. The result is a world of thermal extremes that would be lethal to an unprotected human in either direction. At the lunar equator during the daytime, which lasts approximately 14 Earth days due to the moon's slow rotation, surface temperatures climb above 250 degrees Fahrenheit, 121 degrees Celsius. Hot enough to boil water if water could exist in a stable liquid state at that pressure, which it cannot. The ground itself becomes a radiant heat source. An astronaut standing on the sunlit lunar surface is not only absorbing energy from the sun overhead, they are absorbing it from the ground beneath their boots. The regolith, heated to those temperatures, emits infrared radiation upward into the suit from below. The thermal load comes from two directions simultaneously. Then, the sun sets. And because the moon has no atmosphere to hold any of that accumulated heat, the surface temperature does not gently decline the way it does on an Earth evening. It collapses. Within hours, the sunlit ground that was baking at over 250 degrees Fahrenheit plunges below minus 200 degrees Fahrenheit, minus 133 degrees Celsius. A drop of nearly 400 degrees driven entirely by the absence of any medium to slow it down. The heat that took 14 days of continuous sunlight to accumulate radiates away into the void with nothing to stop it, nothing to catch it, nothing to send even a fraction of it back. This is the thermal behavior of a world without an atmosphere, not a thin atmosphere, not a weak atmosphere, no atmosphere. The moon demonstrates in the starkest possible terms what happens when the only variable in the thermal equation is direct sunlight or its absence. You are either being irradiated by a star or you are radiating into the cosmic background. There is no middle state, but the equator, as brutal as it sounds, is not the worst the moon has to offer, not even close. The moon's rotational axis is tilted only about 1.5 degrees relative to the plane of its orbit around the sun. On Earth, the axial tilt is roughly 23.5 degrees, which is what creates the seasons and ensures that most of the planet's surface receives direct sunlight at some point during the year. On the moon, That tiny tilt means the sun never climbs more than about 1.5 degrees above the horizon at the poles. The light arrives at an angle so shallow that even a modest crater rim casts a shadow hundreds of meters long, and some of those shadows are permanent. Not temporary, not seasonal, permanent in the most literal sense of the word. There are craters near the moon's south pole whose floors have not been touched by a single photon of sunlight in billions of years. They exist in a darkness so total and so enduring that the conditions inside them are unlike almost anything else in the inner solar system. NASA's Lunar Reconnaissance Orbiter, which has been mapping the moon in extraordinary detail since 2009, carried an instrument called the Diviner Lunar Radiometer. Its job was to measure surface temperatures across the moon. When Diviner turned its sensors toward the permanently shadowed regions near the South Pole, the readings that came back startled the planetary science community. Temperatures inside some of these craters measured lower than -410 degrees Fahrenheit, -246 degrees Celsius, roughly 25 to 30 Kelvin. To place that in context, the surface of Pluto, which orbits the Sun at an average distance of nearly 4 billion miles, has a surface temperature of approximately -230 degrees Celsius. The floors of permanently shadowed lunar craters are colder than Pluto. They are colder than the surface of any planet in this solar system. They are among the coldest naturally occurring temperatures ever measured on any solid surface anywhere in the inner solar system, sitting only a few dozen degrees above absolute zero. This fact deserves a moment to absorb. The moon is roughly the same distance from the sun as the Earth. It is our closest celestial neighbor. Humans have walked on it. And yet hidden within craters near its poles are surfaces colder than worlds that sit billions of miles further from the sun. Not because the moon is far from anything, because shadow, in the absence of atmosphere, is absolute. There is no scattered light to warm those crater floors, no reflected infrared from a sky, no convective mixing from warmer regions nearby. The thermal energy budget of a permanently shadowed crater is zero on the input side. The only energy those surfaces receive comes from faint thermal radiation emitted by the crater walls above them and from the even fainter cosmic microwave background. That trickle is so small that the surface equilibrates at temperatures approaching the deep space floor itself. This is why those craters are scientifically precious. They are cold enough to trap and preserve water ice delivered by comet and asteroid impacts over billions of years. Water that would instantly sublimate and be lost to space on any sunlit lunar surface can persist in these shadows for geological ages because the temperature is low enough to keep it stable. The ice does not melt. It does not evaporate. It simply exists in frozen darkness, waiting. It is also why those craters represent one of the most formidable thermal challenges ever faced by human space exploration, because NASA intends to send astronauts there. The Artemis program, which is targeting a crewed lunar landing near the South Pole no earlier than 2028, will place human beings in thermal conditions that the Apollo program never encountered. The Apollo missions landed near the lunar equator, in full sunlight, during the early part of the lunar day. Thermal management was a serious concern even then, but the environment was at least predictable. Sunlit regolith, known solar angles, a clear energy budget. Artemis astronauts operating near the South Pole will face a different situation entirely. They will work in regions where sunlight arrives at extremely low angles, creating long shadows that shift slowly across the terrain. They may approach or enter permanently shadowed regions where temperatures drop to -200 degrees Celsius or colder. The thermal gradient between a sunlit ridge and the shadowed interior of a nearby crater can span hundreds of degrees across a distance a person could walk in minutes. The spacesuits being developed for these missions must handle both extremes simultaneously. One side of the suit might face the sun, absorbing direct solar radiation that tries to overheat the astronaut. The other side might face a shadowed surface, radiating at temperatures cold enough to freeze nitrogen solid. The suit has to manage this asymmetry continuously while the astronaut moves, turns, bends, and works. Russell Ralston, an engineer involved in the development of the Axiom Extravehicular Mobility Unit, the next-generation spacesuit being built for Artemis lunar surface operations, described the challenge with a phrase that captures the scale of the problem. He said that entering a permanently shadowed region on the Moon is something that has never been done before by anything. He called the thermal challenge equivalent to doing a spacewalk inside liquid nitrogen. Liquid nitrogen boils at -196 degrees Celsius at atmospheric pressure. The permanently shadowed craters are colder than that. And unlike liquid nitrogen, which at least provides a uniform thermal environment, the lunar South Pole presents a fractured landscape where the thermal conditions change with every step depending on lighting geometry, surface albedo, and elevation. As of April 2026, the spacesuit development has faced significant delays. A NASA Office of Inspector General report issued just days ago found that both the lunar spacesuit and the microgravity spacesuit are at least a year and a half behind schedule. The original demonstration goals for 2025 and 2026 were described as overly optimistic. If testing follows historical timelines, full spacesuit demonstration readiness may not occur until 2031. The thermal engineering alone, managing the temperature extremes of the lunar South Pole across every joint, seal, glove, and visor of a pressurized suit, is one of the hardest unsolved problems in human spaceflight. The Moon is 250,000 miles away. It receives the same sunlight we do, and yet its thermal environment is so hostile that we have not yet finished building the equipment needed to survive on its surface for even a few hours near the poles. Now consider what happens as you move further from the Sun. Every meter you travel outward from the Sun, the solar energy available to warm you decreases, not linearly. It drops according to the inverse square law. Double your distance from the Sun and the solar intensity drops to 1/4. Triple it and the intensity falls to 1/9. Move 10 times further away and the Sun provides only 1/100th of the energy it delivers at your starting point. At the orbit of Mars, roughly 1.5 times Earth's distance from the Sun, the solar intensity is about 43% of what it is near Earth. Mars does have a thin atmosphere, mostly carbon dioxide, but it provides negligible thermal insulation. Surface temperatures on Mars range from roughly -220 degrees Fahrenheit at the poles in winter to a brief and narrow band near 70 degrees Fahrenheit at the equator in summer. The average sits around -80 degrees Fahrenheit. For a human or a machine on the surface, the diminished sunlight and thin atmosphere create a thermal environment far less forgiving than Earth's, but still within the range of what current engineering can manage, with sufficient power and insulation. Move to Jupiter, 5 times further from the Sun than Earth. The solar intensity is roughly 4% of Earth orbit levels, 25 times less energy available per square meter. The Jovian system is cold in a way that begins to challenge engineering assumptions. Temperatures on Jupiter's moon Europa, a world of intense scientific interest because of the liquid water ocean believed to exist beneath its ice shell, hover around -260 degrees Fahrenheit at the equator, -160 degrees Celsius. The ice surface receives so little solar input that it barely warms above the background temperature of deep space. And yet beneath that ice, something remarkable is happening. Europa's ocean exists not because of the Sun, but because of Jupiter. The immense gravity of the gas giant and the competing pulls of its other large moons flex Europa's interior with every orbit, generating friction deep inside the moon's rocky mantle. That friction produces heat. Tidal heating, as it is called, is one of the only mechanisms in the solar system capable of sustaining liquid water without any contribution from sunlight. The ocean beneath Europa's crust is estimated to contain roughly twice the volume of water found in all of Earth's oceans combined, kept liquid by the rhythmic gravitational kneading of a planet 750 million kilometers from the warmth of the sun. It is a reminder that warmth can exist in the outer solar system, but only through exotic and narrow mechanisms that have nothing to do with the thermal environment a visiting spacecraft or a human explorer would face on the surface. The ice above that ocean sits at temperatures that would freeze carbon dioxide solid. Whatever warmth Jupiter's gravity provides stays locked below, inaccessible to anything standing on the crust. Saturn sits roughly 9.5 times Earth's distance from the Sun. The solar intensity is approximately 1% of near-Earth levels. On Titan, Saturn's largest moon, the surface temperature is around -290 degrees Fahrenheit, -179 degrees Celsius, cold enough that water ice behaves like rock and methane flows as liquid in rivers and lakes. The Huygens probe, which descended to Titan's surface on January 14, 2005, remains the most distant landing ever achieved by a human-made object. It entered Titan's thick nitrogen atmosphere at a speed of roughly 13,000 miles per hour and spent more than 2 hours drifting downward beneath a series of parachutes, measuring temperature, pressure, and composition as it fell. The data it returned painted a portrait of a world operating under thermal rules that inverted everything familiar. The atmosphere was dense, thicker than Earth's, but composed almost entirely of nitrogen and methane at temperatures where those gases occupy the roles that air and water play here. Methane rained from the sky. It carved channels in the ice bedrock. It pooled in vast lakes near the poles. When Huygens finally touched down, its instruments recorded a surface temperature of -179 degrees Celsius. At that temperature, the probe's lithium-sulfur dioxide batteries were already losing capacity to the cold. The electronics were operating near their minimum survival threshold. Huygens transmitted data from the surface for approximately 72 minutes. Then the batteries died. Not from exhaustion in the ordinary sense, from the cold. The chemical reactions that produce electrical current slow as temperature drops. Below a certain point, the battery cannot deliver enough voltage to power the transmitter. Huygens did not run out of energy. It ran out of warmth. The cold reached into the chemistry of its power source and shut it down from the inside. The probe's final signal faded not because its voice gave out, but because the thermal environment of Titan squeezed the life from its only power supply. That story, a machine dying not from impact, not from malfunction, but from the cold stealing the chemical energy that kept it alive, is the outer solar system in miniature. Continue outward. Uranus orbits at about 19 times Earth's distance from the Sun, Neptune at 30 times. The solar intensity at Neptune is roughly 1/9 of what it is near Earth. Almost nothing. The effective temperature of Neptune's upper atmosphere is approximately -353 degrees Fahrenheit, -214 degrees Celsius. The Sun, from Neptune's orbit, is a bright star, brilliant enough to distinguish from the background, several hundred times brighter than the full moon appears from Earth, but insufficient to meaningfully warm anything it touches. And beyond Neptune lies the Kuiper belt, the scattered disk, and eventually the Oort cloud. These are the regions where comets originate, where dwarf planets drift in orbits that take centuries to complete, where the Sun's gravitational influence extends, but its thermal influence does not. Objects in the Kuiper belt, at distances of 30 to 50 astronomical units from the Sun, exist at temperatures around 30 to 50 Kelvin, -220 to -240 degrees Celsius. These surfaces are so cold that most familiar gases, nitrogen, methane, carbon monoxide, exist as solids. They are ices on these worlds, not through any dramatic freezing event, but because the thermal environment has never provided enough energy to melt them. The two Voyager spacecraft are currently the most distant human-made objects in existence. Voyager 1 is roughly 164 astronomical units from the Sun, approximately 15 billion miles away. Voyager 2 is at about 137 astronomical units. Both have crossed the heliopause and entered interstellar space, the region beyond the influence of the solar wind. At these distances, the Sun provides less than 1/40,000th of the energy it delivers at Earth's orbit. For practical thermal purposes, the Voyagers are in the dark. The warmth they retain comes not from the Sun, but from the radioactive decay of plutonium-238 in their onboard radioisotope thermoelectric generators, which produce heat as a byproduct of generating electricity. Even that heat is fading. The plutonium decays on a fixed schedule. Both spacecraft lose approximately 4 watts of electrical power per year. Engineers have spent the last decade progressively shutting down heaters and instruments to keep the remaining systems above their minimum operating temperatures. The critical concern is the hydrazine fuel in the thruster lines. If the propellant freezes, the mission is over. There is no repair crew. There is no second chance. Every decision about which heater to leave on and which instrument to sacrifice is a calculation about thermal survival at the edge of deep space. Just days ago, on April 17th of 2026, NASA sent a command to Voyager 1 to shut down its low-energy charged particles experiment, an instrument that has been operating nearly continuously since 1977. The reason was power conservation. The team hopes the shutdown will buy enough margin to keep the spacecraft alive through its 50th anniversary later this year, when engineers plan to attempt a risky system-wide reconfiguration they have nicknamed the Big Bang, swapping powered components across the spacecraft to extend operations further. If the reconfiguration works on Voyager 2 first, they will try it on Voyager 1. If it fails, these missions that have returned more data about the outer solar system and interstellar space than any other project in human history could end not with a dramatic failure, but with a quiet freezing of a fuel line 15 billion miles from the nearest repair shop. This is what the gradient of distance does. Every step further from the Sun reduces the energy available to maintain warmth. Every step further narrows the thermal margin between function and failure. The Sun does not simply become dimmer as you move away from it. It becomes less relevant. Its contribution to the thermal budget of a spacecraft or a surface drops towards zero, and what replaces it is nothing. Not cold air, not cold fluid, nothing. The cosmic microwave background at 2.7 Kelvin. An environment where the default state of any object is to radiate whatever heat it possesses into an effectively infinite sink and receive almost nothing in return. At the orbit of Neptune, the Sun is a point of light that provides roughly enough warmth to maintain a surface temperature hundreds of degrees below the freezing point of water. In the Kuiper belt, surfaces sit in a permanent twilight, where even nitrogen is a solid. In interstellar space, the only thermal input that matters is what you brought with you. And this brings us to the most uncomfortable realization in this stretch of the story. The gradient does not end. It does not plateau. It does not reach a temperature floor beyond which things cannot get colder. The cosmic microwave background at 2.7 Kelvin is the effective lower bound for any object in the observable universe, because that background radiation is everywhere and provides a minimum input. But 2.7 Kelvin is 2.7 degrees above absolute zero. It is a temperature at which helium can exist as a liquid. It is a temperature at which the thermal energy contained in any substance is so low that the atoms barely move. There is exactly one known natural location in the cosmos measured to be colder than this background. The Boomerang Nebula, a pre-planetary nebula located roughly 5,000 light-years from Earth in the constellation Centaurus, has a measured temperature of approximately 1 Kelvin, minus 272 degrees Celsius. The gas in this nebula is expanding so rapidly from a dying star that it has cooled below the cosmic background temperature through adiabatic expansion, the same process that makes compressed gas cool when it is released from a canister. It is the coldest known natural environment in the entire observable universe, 1 degree above absolute zero, a place where the thermal energy of matter is barely distinguishable from none at all. Between the surface of the Earth, where you sit at a comfortable 300 Kelvin or so, and the Boomerang Nebula at 1 Kelvin, stretches the full thermal range of the natural cosmos. Earth sits at the top of that range, held there by the combined effort of a star, an atmosphere, an ocean, a magnetic field, and 4 billion years of climatic stability. Everything else in the universe is colder. Most of it is profoundly colder. And the only direction the temperature moves, as you step away from a star and into the void, is down. The war between sunlight and shadow is the defining reality of every thermal environment in space. On the surface of the Moon, the war is fought across crater rims and ridge lines, with hundreds of degrees separating the lit from the unlit. In orbit around the Earth, it is fought every 90 minutes as spacecraft spin between day and night. In the outer solar system, the war is already lost. The sun has retreated to a point where shadow is the default state and sunlight is a memory. Every habitat, every suit, every vehicle ever designed for space is a machine built to fight this war. To absorb sunlight without overheating, to retain heat without cooking its occupants, to survive shadow without freezing its systems, to manage a thermal balance that never stabilizes, never becomes comfortable, and never forgives a failure. The machines that do this are among the most extraordinary engineering achievements in human history. And they are the subject of what comes next. Because when one of them breaks, when the system that maintains the balance fails even briefly, the consequences are immediate, cascading, and in some cases, lethal. Space does not wait for repairs. The thermal clock starts the moment protection fails. And the margin between survival and catastrophe is measured in minutes. On May 14, 1973, the United States launched Skylab, its first space station, into orbit aboard the last Saturn V rocket ever to fly. The mission was supposed to mark a new era of long-duration human spaceflight. A permanent laboratory in orbit, a platform for science that would operate for years. It lasted 63 seconds before everything began to go wrong. During the violent shaking of ascent, the station's micrometeorite shield, a thin aluminum skin designed to wrap the outside of the workshop module, ripped away from the hull. It did not simply detach. It peeled back and tangled in the structure, tearing one of the two main solar array wings completely off and jamming the other in a partially deployed position. The station reached orbit crippled. Its primary electrical power was severely compromised. But the electrical damage was not the most immediate threat. The micrometeorite shield had a second function that almost nobody outside the engineering team thought about until it was gone. It was a sunshade. The workshop module of Skylab was essentially a converted upper stage of a Saturn rocket. Its skin was bare metal. Without the shield in place, the direct and unfiltered radiation of the sun hit the exposed hull with its full orbital intensity. And without an atmosphere to distribute or moderate that energy, the thermal consequences were immediate. Within hours, the interior temperature of the workshop began to climb. By the time NASA assessed the situation, internal temperatures had reached 126 degrees Fahrenheit, 52 degrees Celsius. The station was not freezing. It was cooking. And it was cooking not because something had been added, but because something had been removed. The thin layer of shielding that managed the balance between solar input and radiative output was gone. The sun was now depositing energy faster than the station could reject it. The food stored aboard was at risk of spoiling. The atmosphere inside was becoming dangerously hot. Plastics and other materials in the interior began to off-gas, releasing fumes that would have been hazardous to any crew breathing them. There was no crew aboard yet. The first team of astronauts had been scheduled to launch the following day, but their mission was delayed by 10 days, while engineers on the ground scrambled to develop a fix. The solution, improvised under extraordinary pressure, involved the crew of Skylab 2 deploying a parasol sunshade through a small airlock in the hull. The parasol was essentially a folded sheet of reflective material that the astronauts pushed through the opening and unfolded to cover a portion of the exposed workshop skin. It worked. Not perfectly, but enough. The interior temperatures dropped to tolerable levels within hours. Later, during a subsequent mission, a second and larger sunshade was deployed over the first to improve the thermal protection further. Skylab operated for 6 more years before its orbit decayed and it re-entered the atmosphere in 1979. But the lesson of its first day in orbit has informed every major spacecraft design decision since. The lesson was not about micrometeorites. It was not about structural integrity during launch. It was about the fragility of thermal balance in space. A single layer of material, a fraction of an inch thick, had been the only barrier between a habitable interior and a lethal thermal environment. When that layer failed, the entire station became uninhabitable in a matter of hours, not from cold, from heat, from the unrestricted energy of a star with no atmosphere between it and the hull. This is the counterintuitive core of spacecraft thermal engineering. Most people assume that the primary challenge is keeping things warm, fighting the cold, resisting the freezing void. In reality, for spacecraft in the inner solar system, the dominant problem is often the opposite: getting rid of heat, rejecting the energy that the sun, the onboard electronics, and the crew's own metabolic processes pour into the vehicle faster than radiation alone can carry it away. The International Space Station is the most complex thermal management system ever constructed in orbit. It generates heat constantly. The computers, the life support equipment, the communications hardware, the experiments, the lighting, and the 6 human bodies inside it produce thermal energy around the clock. On Earth, this would barely matter. You would open a window, a fan would move air. The heat would convect away into the surrounding atmosphere. In orbit, there is no atmosphere to convect into. The only exit for heat is radiation from the station's exterior surfaces. And radiation alone is not fast enough to handle the load. The station's solution is the active thermal control system, one of the most critical and least discussed pieces of technology keeping the crew alive. The system operates on a principle borrowed from industrial refrigeration but adapted for the unique constraints of vacuum. Inside the pressurized modules, water circulates through a network of pipes called the internal thermal control system. This water absorbs heat from equipment and cabin air through a series of heat exchangers. Cold plates mounted beneath avionics racks draw heat directly from the electronics into the water loop. Cabin air is blown across separate heat exchangers that pull thermal energy out of the atmosphere the crew breathes. But the water cannot carry the heat outside. Water would freeze in the external plumbing if exposed to the shadow side temperatures of the station's exterior. So the internal water loop transfers its thermal load to a second loop at a series of interface heat exchangers. The external loop uses anhydrous ammonia as its working fluid. Ammonia was chosen because it remains liquid across the extreme temperature range encountered in orbit, from the cold of shadow to the warmth of sunlight, without freezing or boiling. The ammonia circulates through an external network of pipes to the station's radiator panels, the large flat structures visible extending outward from the station's main truss. At the radiators, the ammonia gives up its thermal load to space by infrared radiation. The panels are designed with high emissivity surfaces that radiate energy efficiently into the void. The cooled ammonia then circulates back through the system to pick up more heat. The cycle runs continuously. It does not stop. It cannot stop. If the ammonia loop fails, the internal water loop has nowhere to dump its heat. Temperatures inside the station begin to rise. Equipment overheats. If the failure is not corrected, the station becomes uninhabitable. This is not a theoretical concern. It has happened. In 2007, during a spacewalk to reconfigure a portion of the station's power and cooling systems, astronaut Robert Curbeam encountered a malfunction in a quick disconnect fitting on one of the ammonia lines. A stream of ammonia crystals began spraying into the vacuum. Ammonia in its liquid state is toxic to humans. In the vacuum of space, it flash freezes into visible white particles, but the contamination risk to the spacesuit was real. If ammonia residue entered the airlock and then the habitable volume of the station, it could poison the cabin atmosphere. The situation required careful handling, and the crew followed emergency decontamination procedures before re-entering the station. In 2013, a more serious ammonia leak was detected in one of the station's cooling loops. The leak was slow but persistent. Over several weeks, the loop lost pressure. The affected thermal radiator segment had to be bypassed while a repair mission was planned. Astronauts Chris Cassidy and Tom Marshburn performed an emergency spacewalk to replace a pump controller suspected of causing the leak. The repair stabilized the system, but the event demonstrated how close the margin is. A leak in a coolant line, something that on Earth would be a minor plumbing issue, becomes a potential station-threatening emergency in orbit because there is no backup mechanism for dumping heat. There is no opening a window. There is no calling a technician to come by next week. The thermal system is the system. If it goes, habitability follows within hours. The station also carries a network of heaters distributed across its exterior structure. These are not for crew comfort. They exist to keep critical components, fluid lines, mechanical joints, and sensitive instruments from freezing when they pass through the shadow portion of the orbit. Every 90 minutes, the entire station transitions from full sunlight to the shadow of the Earth. During those roughly 36 minutes of darkness, surfaces that were absorbing solar energy are suddenly radiating into the void with no input to replace it. The heaters activate to maintain minimum temperatures on components that would otherwise cool below their operating limits. The power consumed by these heaters is significant. It competes with every other electrical demand on the station. Running a laboratory, maintaining life support, communicating with the ground, and keeping the lights on all draw from the same solar arrays. Thermal management is not an afterthought bolted onto the side of the station's design. It is woven into the fundamental architecture of the vehicle. The size of the solar arrays, the capacity of the batteries, the layout of the truss, the orientation of the radiators, all of these were designed around the thermal problem first and everything else second. Strip the thermal system out of the station's design, and what remains is not a less comfortable space station. It is a collection of aluminum modules that would alternately overheat and freeze every 45 minutes until every system aboard had failed. If you have ever seen a photograph of a spacecraft and noticed that much of its surface appears to be wrapped in gold or silver foil, you are looking at the single most widespread piece of thermal technology in space. It is called multi-layer insulation, and it is on virtually every satellite, every probe, every module, and every telescope ever launched. Its principle is elegant, and its effectiveness is extraordinary. Multi-layer insulation consists of many thin sheets of reflective material, typically mylar or captain, coated with a microscopically thin layer of aluminum or gold, separated by spacers made of a lightweight netting or fabric. A typical blanket might contain 10 to 30 of these layers, stacked together and stitched along the edges. The total thickness of the assembly is usually less than a few centimeters. It weighs almost nothing, and it is one of the most effective insulation systems ever devised for any environment. The mechanism is simple in concept, but profound in execution. In the vacuum of space, where conduction through air and convection are both absent, the only way heat can move through a gap between two surfaces is by radiation. Each reflective layer in the stack intercepts outgoing infrared radiation and reflects most of it back toward the warmer surface. The fraction that is absorbed heats the layer slightly, which then radiates half its energy inward and half outward. The next layer does the same, and the next. Each additional sheet cuts the net radiative heat flow by a fixed fraction. By the time 30 layers have been stacked, the total heat loss from the insulated surface has been reduced to a tiny fraction of what it would be from a bare surface exposed to the void. The gold color that people associate with spacecraft is not decorative, it is functional. Gold is used because it reflects infrared radiation more effectively at certain wavelengths than aluminum does, and because it does not oxidize, which means its reflective properties do not degrade over time. The iconic appearance of spacecraft wrapped in what looks like delicate kitchen foil is actually the visible face of the most fundamental thermal defense available. Without multi-layer insulation, spacecraft surfaces facing away from the sun would cool so rapidly that electronics, batteries, optics, and fluid lines would drop below operating temperatures within minutes of entering shadow. The insulation does not generate warmth. It does not add energy. It simply slows the rate at which the universe takes warmth away. And in space, slowing that rate is the difference between a functioning machine and a frozen one. This same principle applies to every spacecraft ever built, but the specific challenges vary enormously depending on the mission. A satellite in geostationary orbit, 36,000 kilometers above the equator, faces a different thermal profile than one in low Earth orbit. A probe headed for the inner solar system toward Mercury or Venus must deal with solar intensities multiple times higher than near Earth. The Parker Solar Probe, which at its closest approach passes within approximately 6 million kilometers of the Sun's surface, experiences solar intensities roughly 500 times what the Earth receives. Its heat shield, made of reinforced carbon composite, must withstand temperatures above 2,500 degrees Fahrenheit while keeping the instruments behind it near room temperature. The thermal gradient across that single shield is one of the steepest ever engineered by humans. Burning star on one side, functioning cameras and sensors on the other, separated by a few inches of material. A probe heading outward faces the inverse problem: less and less solar energy available, more and more reliance on internal power sources for warmth. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, carried radioisotope heater units throughout its structure. These were small pellets of plutonium-238 that generated heat through radioactive decay, providing thermal energy to keep instruments and propellant lines above their minimum operating temperatures. Without these pellets, the spacecraft's systems would have frozen solid in the diminished sunlight of the Saturnian system, where the Sun delivers roughly 1% of the energy it provides near Earth. The New Horizons probe, which flew past Pluto in 2015 and continues into the Kuiper Belt, uses a similar strategy. Its radioisotope thermoelectric generator provides both electrical power and waste heat that is channeled through the spacecraft's structure to keep critical systems warm. The probe was designed from the start around the assumption that solar energy would be negligible at its operating distance. Every watt of thermal energy it possesses was planned, budgeted, and routed through a deliberate architecture. Now bring all of this down to the most intimate scale of thermal engineering in space, The spacesuit. A spacesuit is a spacecraft for one person. It contains its own atmosphere, its own pressure regulation, its own oxygen supply, its own carbon dioxide removal, its own communications, its own power, and its own thermal control. Every function that a multi-billion-dollar space station performs for 6 people, the suit performs for one, in a package that must also allow the wearer to walk, bend, grip tools, and see clearly through a visor. The thermal challenge of a spacesuit is in some ways harder than the thermal challenge of a station. The station is large enough that its thermal mass provides a buffer. It takes time for the interior of a station to heat up or cool down, even if a system fails. A spacesuit has almost no thermal mass. The astronaut inside is separated from the vacuum by a few layers of material, totaling roughly a centimeter in thickness. The suit's response to changing thermal conditions is nearly instantaneous. During a spacewalk in low Earth orbit, an astronaut rotates through sunlight and shadow along with the station, but the suit's orientation relative to the sun depends on the astronaut's body position. If they are facing the sun, the front of the suit absorbs energy while the back radiates into the void. If they turn, the thermal load shifts. The suit's outer layer is designed with specific optical properties to manage this. The white fabric seen on most spacesuits is not white for aesthetics. It is white because white surfaces reflect a high fraction of incoming visible light while simultaneously emitting infrared radiation efficiently. This combination minimizes solar absorption and maximizes heat rejection, pushing the suit's equilibrium temperature toward a manageable range. Beneath the outer layer, the suit incorporates a liquid cooling and ventilation garment, a full-body undergarment threaded with thin plastic tubes through which chilled water circulates against the astronaut's skin. This garment absorbs the metabolic heat generated by the astronaut's physical exertion and carries it to a sublimator, a device that expels water into the vacuum where it instantly freezes and then sublimates, transitioning from ice directly to vapor. The phase change absorbs a large amount of thermal energy, cooling the returning water before it recirculates through the garment. This sublimation system is elegant but finite. The sublimator carries a limited supply of feed water. When the water runs out, the cooling stops. The duration of a spacewalk is constrained in part by the thermal system's consumables. An astronaut cannot stay outside indefinitely, even if their oxygen holds out, because eventually the suit can no longer manage the heat their own body is producing. The Apollo missions revealed how personal and immediate the thermal problem becomes at this scale. The suits worn by the 12 astronauts who walked on the moon were designed primarily to manage heat rejection. The lunar surface in direct equatorial sunlight was hot, and an astronaut performing physical labor generated significant metabolic heat that had to be removed. The suits had liquid cooling garments connected to sublimators, similar in principle to what is used on the station today. But the suits had no active heating for the extremities. The gloves, the boots, the fingertips, all relied on whatever residual warmth the body provided through circulation and whatever insulation the suit layers offered. When an astronaut turned away from the sun or worked in the shadow of the lunar module, the thermal situation inverted. The cooling system that had been essential moments ago became irrelevant. The hands, furthest from the body's core and least protected by metabolic heat, began to cool. Several Apollo astronauts reported that their fingers went numb during periods of shadow work. The suits could remove heat from their bodies with impressive efficiency. They could not add it back. There was no heating element in the gloves, no warming circuit in the boots. The thermal architecture was a one-way street designed for the dominant problem of the equatorial landing sites, which was overheating. Cold was treated as a secondary inconvenience that the astronaut would tolerate for the brief duration of the excursion. At the lunar South Pole, that hierarchy collapses. Cold is no longer secondary. It is co-equal with heat as a threat, and the suit must manage both simultaneously, in different directions, on different parts of the same body, in real time. Now consider what the Artemis program is asking of its next-generation suit. An astronaut on the surface of the Moon near the South Pole is not in the relatively stable thermal environment of low Earth orbit. They are standing on a surface where the sunlight is low-angle and unfiltered. The ground beneath them may be at 200 degrees Fahrenheit in a sunlit patch and minus 300 degrees Fahrenheit in a shadowed depression meters away. If they walk toward a permanently shadowed crater, the suit must transition from managing solar heat gain to managing extreme radiative heat loss to surfaces colder than any environment the suit was tested against in prior missions. The astronaut's own body heat, which was a problem to get rid of moments ago, becomes the only source of warmth, preventing the suit's components from dropping below their minimum operating temperatures. The suit must handle this transition dynamically, in real time, while the astronaut moves. There is no time to stop, plug in, and recalibrate. The thermal control system must sense the changing conditions, adjust the cooling rate, manage the insulation properties, and prevent localized freezing of suit joints and seals, all while the astronaut is focused on the scientific work they came to perform. If any component of the suit's thermal system fails during a lunar surface operation, the astronaut has minutes, not hours, to return to the lander and repressurize. The suit's low thermal mass means temperatures change quickly. A failed cooling system leads to heat stroke. A failed heating element in a glove operating in deep shadow leads to frostbitten fingers. The margins are thin and the environment does not negotiate. Return now to the Voyager spacecraft, 15 billion miles from Earth, still transmitting, still operating, still managing heat in an environment where the sun is effectively absent. The thermal story of Voyager in 2026 is the story of entropy slowly winning. Both spacecraft carry radioisotope thermoelectric generators that convert the heat of decaying plutonium into electricity. When they launched in 1977, these generators produced approximately 470 watts of electrical power each. The plutonium also produced waste heat that warmed the spacecraft bus, the central body housing the computers, the communications equipment, and the propellant lines. The spacecraft were designed so that this waste heat, conducted through the aluminum structure and augmented by dedicated electric heaters, kept everything above minimum operating temperatures even at the distances of Jupiter, Saturn, Uranus, and Neptune. Nearly 49 years later, the plutonium has decayed enough that each generator produces a fraction of its original output. The electrical power available to Voyager 1 is now roughly 220 watts. The waste heat is proportionally reduced. The interior of the spacecraft bus is colder than it has ever been. The propellant lines that carry hydrazine to the attitude control thrusters are colder than they have ever been. The margin between the current temperature of those lines and the freezing point of hydrazine is measured in single-digit degrees Celsius. Engineers at the Jet Propulsion Laboratory monitor these temperatures from Earth, with a signal that takes roughly 23 hours to arrive. Every few months, they face decisions that involve turning off another heater to free power for a science instrument, or turning off a science instrument to keep a heater running. Each decision is irreversible in practice. Once a heater is turned off and the component it protected cools below its operating temperature, the damage may be permanent. Once a science instrument is shut down, restarting it requires power that may never be available again. The thruster fuel lines are the critical concern. Hydrazine freezes at approximately 2 degrees Celsius, 36 degrees Fahrenheit, a temperature that would feel barely cool to a human hand. But in the thermal environment of interstellar space, where the external temperature is only a few degrees above absolute zero and the only heat source is a fading nuclear generator, maintaining even this modest temperature requires a continuous and precisely managed supply of energy. If the fuel freezes, the thrusters lock. If the thrusters lock, the antenna drifts. If the antenna drifts, the signal from Earth can no longer reach the spacecraft, and the signal from the spacecraft can no longer reach Earth. The mission ends not in an explosion, not in a dramatic failure, but in a quiet drift. A machine that can still think and still listen, slowly turning its face away from home because the heater that kept its muscles from freezing ran out of power. In May of 2025, engineers managed to revive a set of backup roll thrusters on Voyager, one that had been considered dead since 2004. The thrusters had been shut down because their heaters were off, and the team believed the fuel lines feeding them had frozen. A young engineer proposed that the lines might not be frozen after all, that the failure might have a different cause. The team took a calculated risk. They sent a command to restart the heaters. 20 minutes later, temperature telemetry showed the heater temperatures rising. The thrusters fired successfully. The propulsion lead at JPL called it a miracle save. That single episode captures the thermal reality of deep space operations better than any textbook. A 48-year-old spacecraft, a set of thrusters considered permanently dead, a fuel line whose temperature was uncertain because the spacecraft only carries 6 temperature sensors across its entire propulsion system. A team on Earth making a life-or-death decision for a machine 15 billion miles away based on a thermal model, a guess about freezing points, and a willingness to risk the mission on the chance that the cold had not yet won. Every spacecraft that has ever operated beyond the inner solar system has faced some version of this story. The Galileo probe at Jupiter, the Cassini orbiter at Saturn, the New Horizons flyby at Pluto, the Juno orbiter currently circling Jupiter. Each one was designed around a thermal budget that accounted for diminishing sunlight, internal power generation, and the relentless radiative drain of the surrounding void. Each one carried heaters, insulation blankets, radioisotope heat sources, or some combination of all three. Each one was managed by a team on Earth whose primary daily concern, the concern that overrode every scientific objective and every operational ambition, was keeping the spacecraft warm enough to function. This is what people do not see when they look at images of spacecraft floating serenely against the blackness of space. They see a machine. They see an antenna, a camera, a solar panel. They do not see the war happening inside the structure. The constant, silent, unending battle between the heat the spacecraft generates and the heat the universe takes away. They do not see the ammonia loops, the sublimators, the multi-layer insulation blankets, the heater circuits, the thermal coatings, the radiator panels, all working in concert every second of every orbit to maintain a temperature range narrow enough for electronics to function and humans to live. None of this is passive. None of it is optional. There is no spacecraft that survives by simply being well insulated the way a thermos keeps coffee warm. Insulation slows the rate of heat loss. It does not stop it. Given enough time, every insulated object in space will reach thermal equilibrium with its environment, which means cooling to a temperature incompatible with every function human technology depends on. The insulation buys time, the heaters buy time, the cooling systems buy time. All of it is temporary. All of it requires power. All of it is a machine standing between you and an environment that will patiently, ceaselessly pull every joule of thermal energy out of everything you have ever built. The real terror of space is not that it is cold. The real terror is that warmth, in space, is a product of engineering. It is manufactured. It is pumped, circulated, radiated, regulated, and monitored by systems that consume power, wear out, and fail. On Earth, warmth is a given. It is the default state of a world wrapped in gas and lit by a nearby star. The thermal infrastructure of the planet is so vast, so reliable, and so invisible that no human in the history of the species has ever had to consciously maintain it. It simply exists. In space, it does not. In space, every degree of warmth above the background temperature of the universe is a degree that someone built, someone powered, and someone is watching. And when those systems reach their limit, when the power fades, when the coolant leaks, when the heater fails, what remains is not discomfort. What remains is the void, patient, absolute, waiting at 2.7 degrees above the coldest anything can ever be. What remains is to pull all the way back, past the spacecraft, past the suits, past the Moon and Mars and the outer planets, to the full scale of what the thermal emptiness of space means for a species that evolved in the warmest, most protected environment in the known universe, and to the question of what it means that everything we have ever called home was held together by a thermal balance we never had to think about until we tried to leave it. There is a number that appears in nearly every article and documentary ever produced about the temperature of space: 2.7 Kelvin, minus 270.45 degrees Celsius, minus 454.81 degrees Fahrenheit. It is cited so often that it has become a kind of shorthand, a single figure meant to capture the thermal character of the entire universe beyond our atmosphere. Most people hear it, register that it is very cold, and move on without understanding what it actually represents, or why it matters far more than its simplicity suggests. 2.7 Kelvin is not the temperature of space in the way that 72 degrees Fahrenheit is the temperature of your living room. Your living room has air in it. That air has a measurable temperature because it is made of molecules moving at a speed that corresponds to 72 degrees. Space does not work that way. The void between stars contains so few particles per cubic meter that assigning a conventional temperature to it is almost meaningless. What 2.7 Kelvin actually describes is the temperature of the cosmic microwave background radiation, the faint thermal glow that permeates every corner of the observable universe. It is the remnant energy of the Big Bang itself, stretched and cooled over 13.8 billion years of cosmic expansion, until it now washes across all of existence as a nearly uniform bath of microwave photons. Every object in the universe is immersed in this radiation. It arrives from every direction, isotropically, uniformly, without interruption, and it defines the floor. Not a floor in the mechanical sense, not a surface you can touch, but a thermodynamic floor, the lowest temperature that any object in the observable universe can naturally reach. If you took a perfectly insulated sphere, placed it in the deepest void between galaxies, billions of light years from the nearest star, and waited long enough for it to radiate away every last trace of its internal energy, it would eventually settle at 2.7 Kelvin. It could not go lower. The cosmic microwave background would continue depositing energy into it at exactly the rate the sphere radiated energy away, and an equilibrium would form at that temperature, 2.7 degrees above absolute zero, the resting state of the cosmos. Absolute zero itself, 0 Kelvin, minus 273.15 degrees Celsius, is the theoretical limit, the temperature at which all classical molecular motion ceases, no vibration, no rotation, no translation. It has never been reached in nature and can never be reached by any physical process, though laboratories on Earth have cooled materials to within billionths of a degree of it. Absolute zero is a boundary that the laws of thermodynamics forbid from being crossed. 2.7 Kelvin sits just above it, close enough that the distinction feels academic to human experience. At 2.7 Kelvin, every substance you have ever encountered in daily life, every metal, every plastic, every fluid, every biological material is frozen solid. Most gases have long since condensed into liquids and then solidified. Nitrogen freezes at 63 Kelvin, oxygen at 54. Even hydrogen, the lightest and most reluctant element to solidify, freezes at 14 Kelvin. At 2.7 Kelvin, hydrogen is a solid. Helium, the last holdout, becomes a liquid at 4.2 Kelvin under normal pressure and only solidifies under extreme compression. At 2.7 Kelvin and low pressure, helium enters a bizarre quantum state called a superfluid, flowing without friction, climbing the walls of its container, behaving in ways that defy everyday intuition. This is the thermal basement of the universe, the place where the temperature goes when there is nothing left to warm it. And it is not a distant or exotic location. It is everywhere. It is the default state of every cubic meter of space that is not actively being heated by a star, a machine, or a radioactive source. It is what the universe looks like when you subtract the exceptions. Earth is an exception. A temporary, local, magnificent exception. A ball of rock and iron orbiting at exactly the right distance from exactly the right kind of star, wrapped in a blanket of gas thick enough to trap outgoing thermal radiation, wet enough to store and redistribute enormous quantities of heat, and magnetically shielded enough to keep that blanket from being stripped away by the solar wind. The surface temperature of Earth averages roughly 288 Kelvin, 15 degrees Celsius, 59 degrees Fahrenheit. Compared to the 2.7 Kelvin baseline of the universe, Earth is a furnace. A tiny pocket of extraordinary warmth, sustained by a chain of physical circumstances so specific and so interdependent that altering any single link would render the surface uninhabitable. Take away the atmosphere and the surface temperature plunges, not to the comfortable average of 15 degrees Celsius, but to approximately minus 18 degrees Celsius as a global mean, and far worse than that in practice. Without the greenhouse effect, without the thermal inertia of the oceans, without convective circulation to move heat from the equator toward the poles, the planet's surface would swing between scorching days and frozen nights in a pattern resembling the moon. Take away the magnetic field, and the atmosphere itself begins to erode, sputtered away by charged particles from the sun over geological time, as happened to Mars. Take away the oceans, and the planet's thermal mass collapses, removing the moderating influence that keeps coastal climates mild and prevents temperature extremes from becoming immediately lethal. Each layer of Earth's thermal infrastructure supports the others. Together, they create a stable, warm, livable environment. Alone, none of them is sufficient. Humans evolved inside this system. Every biological process in your body is calibrated to it. Your core temperature is maintained at approximately 37 degrees Celsius, 98.6 degrees Fahrenheit, by a network of physiological responses so automatic that you never consciously engage them. When you are too warm, you sweat. The evaporation of moisture from your skin carries heat away. When you are too cold, you shiver. The involuntary contraction of your muscles generates heat. Your blood vessels constrict or dilate to regulate how much thermal energy reaches your skin. Your metabolism adjusts its rate to match demand. All of this happens without your awareness, without your permission, and within a narrow operating range that feels enormous from the inside and is laughably small from the outside. The difference between the hottest temperature a human can survive and the coldest, even with extreme physiological adaptation, spans perhaps 100 degrees Celsius under the most generous conditions. The thermal range of the natural universe spans from near zero to hundreds of millions of degrees inside stellar cores. Humanity's survivable window is a sliver so thin it would be invisible on a graph drawn to scale. And every inch of that sliver is maintained by the planet. When you leave the planet, you leave the system, all of it, at once. There is no partial departure. There is no gradual transition from protected to unprotected. The atmosphere does not thin out gently over thousands of miles, offering you incrementally less support. It thins out over a few hundred kilometers, and then it is gone. The Kármán line, the internationally recognized boundary of space, sits at 100 kilometers above sea level. At that altitude, the air is so thin that aerodynamic flight is no longer possible. A few hundred kilometers higher, in low Earth orbit, the residual atmosphere is measured in individual molecules per cubic centimeter. For all thermal purposes, you are in vacuum. The entire transition from the warmest and most stable environment in the known universe to the most thermally hostile takes place across a distance that you could drive in a car in about an hour. And beyond that line, every thermal comfort you have ever known becomes something you must build, carry, power, and defend. Consider what this means for the future of human expansion beyond Earth. Every plan for a permanent presence on the Moon, on Mars, or anywhere else in the solar system is fundamentally a thermal engineering problem. The biology is secondary. The psychology is secondary. The rocket science is, in a certain sense, secondary. Because none of it matters if you cannot keep the habitat warm enough for humans to live and cool enough for equipment to function continuously without interruption for years and decades at a time. A lunar base near the South Pole would face a thermal environment that alternates between direct low-angle sunlight and shadow, with the permanently shadowed craters nearby sitting at temperatures approaching 30 Kelvin. The habitat would need to manage solar heat gain during illuminated periods, radiative heat loss during shadow periods, and the extreme thermal gradient of the surrounding terrain at all times. Heating the interior is not the hard part. Any electrical system generates waste heat. The hard part is controlling the flow, preventing heat from leaking out through the structure into the regolith below, preventing the cold of the lunar surface from conducting inward through the habitat's foundations, managing the thermal expansion and contraction of structural materials that cycle through hundreds of degrees of temperature change with every shift between light and dark. On Mars, the challenges are different but no less severe. Mars has an atmosphere, but it is roughly 1% the density of Earth's. It provides almost no convective insulation. A person standing on the Martian surface in a suit would lose heat primarily through radiation, just as in vacuum, with a minimal contribution from the thin carbon dioxide air. Surface temperatures at the equator can reach a relatively mild 20 degrees Celsius at noon during summer and then drop to -73 degrees Celsius overnight. At the poles during winter, temperatures fall below -140 degrees Celsius. Any habitat on Mars must be designed to handle these extremes while drawing power from solar arrays that receive less than half the energy available in Earth orbit, or from nuclear sources that carry their own mass, complexity, and political challenges. The outer solar system is a thermal frontier that no human has ever approached and that current technology is barely equipped to address robotically. A crewed mission to Europa, orbiting Jupiter at roughly 5 times Earth's distance from the Sun, would need to provide all heating internally. Solar panels at Jovian distances produce a fraction of the power they generate near Earth. Radioisotope systems or compact nuclear reactors become the only viable energy sources. The habitat, the suits, the vehicles, every system exposed to the exterior environment would need to be designed for sustained operation at temperatures below -150 degrees Celsius. Seals become brittle, lubricants solidify, metals contract, electronics slow. Every material property that engineers rely on at room temperature changes at cryogenic conditions, often in ways that reduce reliability and increase failure rates. And yet there is something about these challenges that reveals the deeper truth this entire story has been building toward. The problem is not that space is cold. If space was simply cold, the way a winter in Siberia is cold, the engineering would be straightforward. You would insulate more, heat more, and carry thicker coats. The problem is that space is thermally empty. It does not offer a stable environment to insulate against. It offers nothing. The thermal condition of any object in space is determined entirely by what that object does to itself and what the sun does to it. There is no baseline, no floor that feels like a floor, no default state that a human body or a human machine can rest in without active intervention. On Earth, if every heating system in your city failed simultaneously on the coldest night of the year, you would not die immediately. The buildings retain heat, the ground retains heat. The air, even cold air, has thermal mass. You could survive for hours, possibly days, in an insulated structure with no power, bundled in clothing, eating stored food, waiting for help. The thermal infrastructure of the planet buys you time even when your personal infrastructure fails. In space, if your thermal system fails, the clock starts immediately. In a spacesuit, the timeline is measured in minutes. In a small spacecraft, perhaps hours. In a large habitat, perhaps days. But the direction is always the same, toward equilibrium, toward the temperature of the surrounding environment. And the surrounding environment is 2.7 Kelvin, or whatever local modification the sun provides. There is no calling for help that arrives in time. There is no waiting it out. There is no thermal inertia of the surrounding world to lean on. There is only what you brought and how long it lasts. This is why thermal control is not one engineering discipline among many in spacecraft design. It is the discipline. It is the one that determines whether everything else gets to function. A computer that overheats stops computing. A fuel line that freezes stops flowing. A seal that contracts beyond its tolerance starts leaking. A battery that drops below its operating temperature loses capacity and may never recover it. A human being whose core temperature drops by just a few degrees loses cognitive function. A few degrees more, and cardiac arrhythmia begins. A few degrees beyond that, death. The thermal margins of space technology are measured in degrees, single degrees. The difference between a functioning thruster and a frozen propellant line on Voyager is a handful of degrees Celsius. The difference between a stable cooling loop on the space station and an overheating cascade is a few degrees of fluid temperature rise. The difference between a safe spacewalk and a medical emergency is a few degrees of core body temperature change inside the suit. Every one of these margins is maintained by a machine. Every machine requires power. Every power source is finite. There is a way of seeing all of this that changes how the universe feels when you look at it. On a clear night, away from city lights, the sky is filled with stars, thousands of them visible to the naked eye, millions more through a modest telescope. Each one is a furnace, a thermonuclear engine converting hydrogen to helium and flooding the surrounding space with photons. They seem abundant, generous. The sky appears full of light and warmth. It is an illusion of perspective. The stars are points. The space between them is vast beyond comprehension. The nearest star to the Sun, Proxima Centauri, is 4.25 light-years away. That is roughly 40 trillion kilometers. The light and heat from Proxima Centauri that reach our solar system are so diluted by that distance that they are indistinguishable from the cosmic background. The Sun dominates the thermal budget of everything within a few billion kilometers of it. Beyond that, its influence fades toward irrelevance, and between the Sun and Proxima Centauri lies 4 light-years of void at 2.7 Kelvin. The galaxy is not warm, it is not lit. It is a scattering of furnaces separated by unimaginable gulfs of nothing. The space between stars is not a room with dim lighting, it is an abyss. An environment where the thermal energy density is so low that a cup of warm coffee, if it could somehow be suspended in interstellar space without a container, would be among the warmest objects for light-years in every direction. The heat in that single cup would radiate away over hours and days, and nothing in the surrounding void would replace it. The coffee would cool, freeze, and eventually reach 2.7 Kelvin, and it would remain at that temperature for the rest of the life of the universe, unless something intervened. That image, a warm object cooling in the dark with nothing to stop it, is the fundamental thermal story of everything that exists. Stars burn and die, their heat disperses, the universe expands and cools. The cosmic microwave background, already at 2.7 Kelvin, continues to drop as the expansion of space stretches its wavelengths further toward oblivion. In the far future, the background temperature will approach zero asymptotically, never quite reaching it, the last whisper of the Big Bang fading across an ever larger and ever emptier cosmos. Everything warm is temporary. Every star, every planet, every lit and heated room, every living body maintaining its 37 degrees against the dark, all of it is temporary. All of it is a local reversal of the universal trend, a brief island of warmth in an ocean that is cooling toward the lowest temperature physics allows. This is not a poetic statement. It is the second law of thermodynamics expressed in cosmological terms. Entropy increases, heat flows from hot to cold, concentrated energy disperses. The universe moves from order to disorder, from hot to cool, from structured to diffuse. Every machine that maintains a warm habitat in space is fighting this law, not breaking it. You cannot break it. Just locally and temporarily reversing it at the cost of energy that must come from somewhere, and that will eventually run out. The Earth itself is fighting this law. The sun provides the energy. The atmosphere traps enough of it. The oceans store and circulate it. The result is a world where liquid water can exist on the surface, and biological chemistry can operate, and a species can emerge that looks up at the sky and wonders why it is so dark and so cold out there. The answer is that dark and cold is what the universe is. Warm and bright is the exception. We are the exception. This planet is the exception, and every step we take away from it carries us closer to the rule. There is a passage in the engineering documentation of nearly every deep space mission that rarely makes it into public discussion. It is the section of the thermal analysis that describes the end-of-life scenario. What happens when the power runs out? What happens when the last heater turns off? What happens when the spacecraft, the habitat, the suit, can no longer maintain its thermal defenses against the surrounding void? The answer is always the same. The object cools, slowly at first, then faster as the thermal gradient steepens. Internal components contract, fluids freeze, seals crack. Electronics cease to function. The structure reaches thermal equilibrium with its environment, which in deep space means approaching the cosmic background temperature. And there it stays, not for years, not for centuries, for the remaining lifetime of the universe. A frozen artifact, a monument to the brief period during which something warm existed inside it. The Voyager spacecraft will reach this state eventually, when the last watt of power fades from their generators, when the last heater switches off. The spacecraft will cool over days and weeks until they match the interstellar medium. Their golden records, the messages from Earth encoded on gold-plated copper discs, will endure at cryogenic temperatures in the vacuum for billions of years. The data engraved on them will outlast every structure on Earth, but the machines themselves will be silent, cold, and dark, drifting through a void that never once cared whether they were warm. Everything humanity sends into space carries this future inside it. Every satellite, every probe, every discarded rocket stage, every bolt and panel and fragment of debris will eventually reach thermal equilibrium with the void. The warm, active, transmitting phase of any human object in space is the anomaly. The cold, silent, drifting phase is the default, and the default lasts forever. This is the terrifying reality of how cold space really is. It is not a number. It is not a temperature that can be printed on a chart and compared to a winter day in Antarctica. It is a condition, an environment where warmth does not exist unless something creates it, maintains it, and defends it against a universe that is under no obligation to help. On Earth, you are warm because the planet is warm, because the air is warm, because the ground is warm, because 4 billion years of thermal infrastructure built by a star and an atmosphere and an ocean and a magnetic field conspire every second of every day to keep the surface of this world within a narrow band of temperatures compatible with liquid water and living tissue. In space, you are warm because a machine is running, because a pump is circulating coolant, because a heater is drawing power from a generator, because a layer of insulation is slowing the inevitable loss, because an engineer on the ground is watching a temperature readout and making decisions about which system to sacrifice so that the critical ones survive another month. The moment the machine stops, the warmth begins to leave, and nothing in the surrounding universe will bring it back. That is the truth buried beneath the simple phrase, "Space is cold." It is not cold the way winter is cold. It is cold the way absence is cold. It is the thermal expression of emptiness itself, a vacuum that cannot carry heat, surrounding objects that are either bathed in the unfiltered fire of a star or radiating into a sink barely above absolute zero, with nothing between those extremes and no natural mechanism to moderate either one. The human species evolved in a cradle, a warm, pressurized, magnetically shielded, atmospherically buffered cradle that handled every thermal challenge on our behalf for the entirety of our existence. We never had to think about where the warmth came from because it was always there. It was the air. It was the ground. It was the sunlight filtered through 100 kilometers of gas that turned a thermonuclear blast into a pleasant afternoon. Space strips that cradle away and shows you what was always underneath. A universe that is almost entirely cold, almost entirely dark, and almost entirely empty. A universe where warmth is rare, local, temporary, and artificial once you leave the one world that provides it for free. Every astronaut who has looked out of a window at the blackness beyond the station has seen it. Every engineer who has managed a thermal system on a spacecraft millions of miles from home has felt it. The understanding that the warmth inside the cabin, inside the suit, inside the habitat, is a human construction. Fragile, finite, a thin, bright line drawn against an infinite dark background. And beyond that line, patient and permanent and older than any star in the sky, the cold waits. Not with malice, not with intent, just with the simple, bottomless indifference of a universe that was never warm to begin with, and that will be cold long after the last star has gone out, and the last machine has stopped, and the last degree of heat has radiated away into the expanding dark. That is the terrifying reality of how cold space really is. Not a number, a condition. The default state of everything that exists, interrupted only briefly, only locally, only temporarily, by the fragile and extraordinary exception of warmth. And we are standing in that exception right now, wrapped in atmosphere, held by gravity, warmed by a star, breathing air that carries the heat of a planet that has been managing its thermal balance since before life existed. The moment we step beyond it, we carry nothing but what we build, and the universe outside has all the time there is,